Dear students, welcome to all of you in today's lecture series, and current lecture is lecture number 20, where we will be going to discuss what are the various design steps which we can adopt, which we can follow while doing any design of simply supported two-way slab, and all the steps will be based on the guidelines mentioned in IS 456 2000. Let us go through the various steps which we have to follow in case of a design of simply supported two-way type of RCC slab, so that a design should be safe as well as economical. Here the steps we have selected in such a way that all the guidelines or recommendation of IS 456 2000 should be taken care of. And here in step number 1, as usual, we have to pick what is the grade of material, so that we can decide what should be the grade of concrete as well as grade of steel. Now, if this information is available in the problem statement, then we can directly pick what is the grade of concrete and steel from the design statement. And otherwise, if the information is missing, then we can assume based on the guideline of IS 456 that what should be the minimum grade of concrete as per the exposure conditions, and what should be the grade of steel and what type of steel we have to taken in the design. And in step number 2, here we are going to discuss that how to decide or how to evaluate what should be the effective span of the slab. We can refer clause number 22.2 here. First of all, let us discuss about the width of the slab. And for design calculation, as in one-way slab we have discussed in the design of one-way slab, similarly here same pattern we have to adopt. That means we will be selecting a strip in the middle of the slab, since it is a simply supported type of slab. So a strip of 1000 millimeter we will be picking, and here how it is different from one-way slab. Here we have to take both the directions into consideration. That means both the span, whether it is longer span or shorter span. So ultimately what we have to do, we have to design a 1 meter strip of the slab which is parallel to the shorter span, as well as another strip of a same 1 meter width in the direction of the parallel to the longer span. So that means both the strips will be in transverse to each other. And the second point is how to evaluate or how to do the calculation for effective span of slab. So here same type of a guideline or which we have used in case of a one-way slab, or either in case of a singly reinforced beam. So same information or same type of calculation we have to do in case of simply supported two-way slab. So that means for simply supported slab is our case, slabs that are not built integrally with its supports, and they are directly placed on the brick walls. So these type of slabs, as we are well aware that they are coming under the category of simply supported slab. So how to calculate the effective span? So here again we have to follow the same guideline. First of all, we have to calculate effective span, that is equal to LC plus D, where LC is the clear span length between two supports, and D is the effective depth of the slab, which we are going to decide later on. And then second point, we can take effective span may be equal to center of the support. So whatever the least value out of these two parameters that we can take into consideration, so that will be the. Now in step number 3, what we have to do, we can decide what should be the thickness or depth of the slab, and we have to refer clause number 24.1. Okay, so now the thickness of the two-way slab can be decided based on the deflection criteria as usual, similar to that which were considered in the design of beams, or you can say design of a one-way slab also. So first of all, first point is checking the actual deflection against the allowable limits. And the second point will be based on the maximum span to depth ratio, that is L by D ratio specified for serviceability criteria, which can be assumed to be not exceeding span by 250. So based on these 2 points, we can first of all decide what should be the thickness of slab, which we can take as a trial, and later on, after doing the various calculation and applying various checks, we will be just came to understand that whether our assumption is correct or not. So accordingly the section can be revised. So overall thickness of the slab, that is capital D, we can say can be evaluated as it is equal to the sum of effective span plus clear cover and half of the bar diameter, the main reinforcement. Here we have to keep in mind that whenever we are doing any calculation, and since there are two span Lx and Ly, so what we have to take into consideration, we will be focusing on shorter span. So that means when we are going to calculate this effective uh, depth of the slab or overall depth of the slab, then we have to take into consideration the center line of the main reinforcement, that is which is along the shorter span. And a clear cover again we can take as per the requirement based on the information available in clause number 26.4, based on what is the exposure condition and what should be the minimum clear cover required. And similarly, another guideline is diameter of steel bar, maximum diameter of steel bar should not be greater than 1/8 of the total thickness of the slab, that is overall thickness of the slab. And we can refer clause number 26.5.2.2 here. Now in continuation to step number 3, where we have discussed about the thickness of slab, and a very important part of this step is that how to decide what should be the effective depth of the slab, and we can refer clause number 24.1. And based on this value which we will assume for effective depth of the span, we can later on calculate overall depth of the slab. Now vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the value mentioned here onward. It may be the case of a beam or it may be case of a slab which is having uniform thickness. So deflection generally we can limit as per the following guidelines. So case number 1 we can see as in reference to clause number 23.2.1. That means we can take basic value of span to depth ratio when the span length is, that means shorter span having length up to 10 meters, then we can take it as a case number 1, and we can take the L by D ratio equal to 20, as normally we have taking in case of beams also. And if for span is greater than 10 meters, then accordingly we can multiply it with a factor, that is 10 by span length. And by this step we will be able to get span by D ratio. And these basic values, that is L by D is equal to 20, it need to be multiplied by a modification factor, that is KT, and that KT factor will depend upon the area of steel as well as the stress of the tensile steel. And for this we can take the value from figure number 4 of IS 456. Now in reference to clause number 24.1, that means if we consider it as a case 2, then if you refer clause number 24.1 and in the notes part, you will find this information. That first point is for slabs which are spanning in two directions, that means two-way slab, the shorter of the two spans should be used for calculating the span to effective depth ratio. So that means here a very important point is that X by D ratio when we have to calculate, then this Lx should be the shorter span length. So here since we have two type of span, one is shorter and another is longer span. So for the calculation purpose, we will always take shorter span as Lx and a longer span Ly. Now for two-way slabs having shorter span, if this condition is satisfied, that means the shorter span is having span length up to 3.5 meter, and if you are using mild steel reinforcement, then span to effective depth ratio can be taken as or can be assumed, which is considered to be satisfying the vertical deflection limit. And another condition is for loading class up to 3 kilonewton per meter square. So then span to effective depth ratio we can take in case of a simply supported slabs, since we are going to discuss all the guidelines regarding simply supported. So Lx by D ratio we can take equal to 35. And keep in mind this ratio can be taken when uh, reinforcement which you are taking, that is a mild steel. Now, if you are using high strength steel as normally in practice we use, then having grade Fe 415, then our value, that is value 35, we can multiply it by a factor, that is 0.8. So that means if a second case is of in your problem, that means having shorter span length less than or maybe equal to 3.5 meter, and if loading condition is this much, then you can take Lx by D 35 instead of 20. And since we are using high strength steel normally, so then this 35 will be multiplied by 0.8, so that will become the Lx by D ratio. Again, to remind you that Lx is the length of the shorter span. Now step number 4, here we are going to discuss that what should be the loading calculation, how to do the loading calculation. So again, since we have decided that whether it is a one-way slab or two-way slab, we will be designing a wide strip, that means a strip of slab having 1 meter width. And so that's why we are taking this into consideration for loading calculation. So self weight of slab based on the information which we have decided in the previous steps. So self weight of slab per meter length we can calculate just like one way slab. So W dead load we can say it is calculated based on the assumed dimension in the previous steps, and the unit weight of a concrete, or better we say unit weight of a RCC, that we generally take 25, and capital D will be the overall depth of the slab, and the V width is the 1 meter. So we can calculate the dead load in units of a kilonewton per meter square. Then load of niches. If information is available in the statement, then no issue. We can take directly the same value. But if finishing load is not provided, then we may refer IS, it is IS 875 part 1. It was wrongly written IS 857. It is 875 part 1, which can be referred. And similarly, live load on the slab, if it is not provided, again here is you have to make the correction, that is 875 we can take, and part we can refer, that means IS 875 part 2 we have to refer. So from that information in part 2 or information available in the statement, we can take live load in the form of UDL, that is in the unit of kilonewton per meter square for 1 meter strip of having 1 meter width. So ultimately total factor load we can calculate, that is WU, which will be equal to sum of dead load, that is self weight of the slab, then weight of the finishes, and live load whatever we, and we are multiplying it with a partial safety factor, that is 1.5. So ultimately we are able to get the what is the total factored ultimate load for the design of the two-way slab in step number 4. So now in step number 5, what we are going to discuss, that how to calculate bending moment as well as shear force. And here we have to refer Annexure G clause 2.1 of IS 456, where the calculation for bending moment per unit width for a simply supported two-way slab, and code is recommending the method of bending moment coefficients. So that means bending moment coefficients are available in Annexure G 2.1. For calculation of bending moment, again we have to consider shorter span length, that is Lx. For all type of calculation, we are going to take Lx that is equal to the whatever be the value of the shorter span length. So by using these equations, that is mx is equal to alpha x w u lx square and the my, that is given by alpha y w lx square, where mx and my are the bending moment on the strip of unit width spanning along x direction, that is along shorter span as well as along longer span. And alpha x and alpha y are the bending moment coefficients which we can take from table number 27 of IS 456. And WU is the uniformly distributed factor load on the slab which we have calculated in step number 4. And Lx and Ly, as we have discussed earlier also, are the length of the short and longer span respectively. And this is a snapshot of table number 27, and you can see the title of this table is bending moment coefficients for slabs spanning in two directions at right angle simply supported on four sides. So this table number 27 is applicable when we are going to design a two direction slab. That means a two-way slab, in simple language we can say two-way slab which is simply supported. And so here we have to get the information, that is value of alpha x and alpha y based on Ly by Lx ratio. So first of all, we have to calculate what is the ratio of Ly by Lx, and based on that value, whether it is 1, 1.2 or etc., or in between these two values, then accordingly we can do the interpolation, and we can find out the value of alpha x from this row as well as alpha y from this row corresponding to the value of Ly by Lx. So after step number 5, let us go to step number 6, and this is also one of the very important step. We can say that we have to apply the check for adequacy of the depth provided. So earlier we have assumed effective depth as well as over depth for the slab. So here in this step number we will be able to check whether that depth which we have provided is adequate or not. So depth of slab adopted earlier need to be checked, as I told, for adequacy to register the ultimate bending moment MU, considering the section as a balanced type of section. So you can see that this is a slab which is supported on all the four sides, having longer side Lx, Ly, and a shorter span Lx. So what we have taken into consideration, since it is simply supported type of slab, so we have to take two strips having 1 meter width each at the center of the slab. One is spanning along the parallel to the Lx direction and another will be spanning parallel to the Ly direction. So whatever the calculation, reinforcement, bending moment, etc. we are doing, that will be, we are designing these two strips, and ultimately as similar to one-way slab, whatever the reinforcement we get, that will be taken or adopted throughout the slab in along both the direction, that is along Lx direction parallel to Lx as well as parallel to Ly. So the required depth of the slab we can calculate, and here since we are getting the two values of bending moment, one is bending moment mx and other is my, and that is based on the both the span direction individually. So how to calculate the depth required? So first of all we will be calculating the depth required based on the bending moment along x direction, as well as dy is the effective depth required based on the bending moment along y direction. So both can be calculated from the equation which we have taken in the previous step. Also, equation for the moment of here, what we are going to discuss, we will be using the moment of resistance equation for a balanced section, as we have taken in case of a singly reinforced beam. Now mx and my we can use, which we have uh, received or we have calculated in step number 5. And whatever be the higher depth we got from in the form of dx as well as dy, so higher value of dx and dy will be taken for the design purpose. So mu max we are given by we can take by this formula, that is 0.138 FCK BD square. Here again width of the strip will be 1000 millimeter. So based on the information, that is FCK grade of concrete width, it is equal to 1 meter, we can work out what should be the depth required to take care of this much of bending moment. So the depth obtained, so that means higher value must be checked against the depth of the slab provided. So this is the depth required which we got from this equation. And in the previous step, whatever the depth we have provided, so we have to compare these two values along with the check of section, so that whether it is under reinforced or over reinforced. So this step for check for under reinforced, that we are already aware we have applied in case of a singly reinforced beam as well as one way slab. So whatever the value we got, dx and dy, we will be taking average out these two. So average value will be noted down. In step number 7, we will be going to discuss that how to calculate the area of reinforcement required. So here, tensile reinforcement required, that is AST. We have to do the calculation along x direction as well as along y direction, or in other word we can say along shorter span as well as along longer span. So area of reinforcement, whatever required to resist the ultimate bending moment, mu can be calculated by using the same equation of singly reinforced beam section. That is, you can use this formula where mu will be the ultimate moment, maximum bending moment, and Fy is the yield strength of steel which you are going to use, area of steel, and other parameters we are already aware. So based on this equation and whatever the information available with us, we will be able to work out what is the area of steel required. And area of tension steel can be worked out with the help of a mentioned equation for both mx and my, that is bending moment along x direction as well as along y direction. And accordingly, we will be able to decide what should be the bar diameter, and they are to be arranged in the slab throughout the span at a suitable spacing. Now here one thing we have to note down carefully, that whatever the area of steel we are able to get here, that area of steel is calculated for 1000 millimeter strip as already mentioned. So similar steel extended throughout the span of the slab in both the direction, along shorter span as well as along longer span. And the required spacing between these parallel bars we can calculate for 1 meter width of the strip as follows, which we have already discussed in the previous classes also. So that means required spacing you can work out by this equation. This is the width of the strip and the area of one bar which we have assumed in the earlier sections, and the area of steel required which you will be getting from this formula. Now the reinforcement is to be provided as per the required spacing after applying the check for limit of area of steel. That means what are the limit of area of steel are recommended by IS code, as well as spacing limits which you can get from 26.5.2 clause as well as 26.3 of IS 456. Now let us go through the information regarding bent of bars. So important point again, even we have discussed the same detail in the one-way slab. So as we know that tensile steel which we have decided, that is based on the maximum value bending moment, and maximum bending moment will be obtained at the mid of the span, since it is a simply supported type of slab, and it will be decreasing towards the support, and ultimately bending moment is zero at the simple support. So we can say that whatever the tension steel we have decided or we have calculated for the mid of the span, that is not required at the support level because their bending moment is 0. So minimum steel is required to be provided there. And again, it will also take care of economy. So 50% of the bars we can bend up. And so every alternate bar can be bent up and extended to the top of the support, and which also will be helpful in taking care of a shear stress capacity. That means shear stress capacity of the beam or slab will also be able to increase. And the bent up bars we have to uh, bent up at a distance 0.1 and into span length from the edge of the support. And this will be the diagram which will be applicable in case of a two-way slab. So that means you can see that both the steel, one steel is along the shorter span, another steel will be along the longer span. So here in case of a two-way slab, we are not going to provide any distribution steel, and these bent up bars are lifted at a distance 0.1 L from the both sides. So that means we can take it up to the top level of the slab and up to the support section. So this will be the diagram of uh, one span, you can say. Similarly, these bars will be later on will be bent up in the other direction also. Now in step number 8, we are going to discuss how to apply the check for deflection, and we can refer clause number 23.2.1 here. Check for deflection is to be applied along shorter span. So here again you have to keep in mind that means when you are applying the check for deflection, then you have to take into consideration the shorter span since it is more critical as compared to longer span. So here Lx by d ratio we will be able to find, and that should be lesser than 20 into kT. Again, similar to one way slab, this kT value we can obtain from figure number 4. This is figure number 4. So based on this figure which is available in IS 456, we can calculate this modification factor, that is kT, and for this we require percentage of tension steel, and then modification along the y direction you can pick based on two parameters. One is the percentage of steel you can see along the x-axis, and other will be the tensile strength of the steel, and based on the various curves you will have to pick the curve which is belonging to your calculation. And for this calculation of kT, what we have to do, we have to refer this figure, and based on the value of FST, which is written as here FS, that is the steel stress of service loads, and percentage of steel value, that is along x-axis, percentage of tension steel we have to work out. FST you can just work out from the formula given here, that is 0.58 into Fy and into the ratio of area of steel required to the area of steel which you have provided. In case of this check is not okay, then what we have to do, we have to go for the redesign of the section as per our requirement. Now after check for deflection, in step number 9 we have to apply for check for shear. Again you can refer this clause number 40 of IS 456, and the check for this section for shear stresses is always taken as a critical section, and the critical section is at a distance that is equal to effective depth. Here what we will take, this effective depth will be, we will be taking the value of average depth which we have calculated in the previous steps, and that means we have to locate the critical section at a distance that d will be termed as d average from the face of the support. Here we have to calculate the nominal shear stress first of all, that will be given by this formula available in IS 456, and here we width of the slab we have to take into consideration, that is 1000 millimeter, and we have to obtain value of tau c from table number 19, which is the design shear strength of the section based on the concrete as well as steel, and then we have to multiply it with k, and this for this evaluation of this value of k you can refer clause 40.2.1.1. So now design shear strength in case of two-way slab will be we have termed it as tau c dash, that is equal to tau c into k. And in first case, if the value of tau c dash which we have calculated here, if it is greater than tau b, that means then we can say the section is self-sufficient to take care of shear stresses. Again, as per IS code provision, we have to provide minimum shear reinforcement as per clause number 40.3. But here in this type of two-way slab, as in one-way slab, I have explained to you that we have to apply the check for shear, and most of the cases you will find that slab is always safe in shear, so you need not to require to provide any shear reinforcement. And the second condition, again, as we have discussed in the one-way slab also, if tau v exceed half the value of tau c max, and tau c max we will be getting from table number 20. So based on the codal guideline, you have to check it. If this happen, then the section may be required to redesign. Now, if this third condition is satisfied, that means 0.5 tau c max is greater than tau v and greater than tau c. That means the section which you are going to design, it has to resist this much shear stress which is greater than tau c. That means we need to provide the shear reinforcement. So ultimately, shear reinforcement need to be designed as per clause number 40.4 if this type of condition happen. Now in step number 10, we have to apply the check for development length. Again, you can refer same guideline that were already available in case of one-way slab. That is clause number 26.2.1 we can refer. And the development length required is given by formula LD is equal to 5 sigma s upon 4 tau BD. Which you are well aware, so I'm not going into detail. Phi is the nominal diameter of bar, sigma s is the stress in bar at the section under consideration at design load. Tau BD is the design bond stress, is given in table which is available in clause number 26.2.1.1. And this development length also include anchorage value of hooks. If we are providing any hooks, in general, in case of mild steel type of reinforcement, we are providing hooks, but in case of high strength steel, we are not providing hooks. We are just bending the bars at the support level. Now we have to apply the check. First of all, what is the embedment length of the reinforcement bar into the support can be possible. So again, you can refer previous lecture also. That mean what is the embedment length which can be possible so that reinforcement can be taken up to that section. And this formula you can take into calculation that LE is width of the support minus clear cover as per the codal requirement. And as per IS 456, this LE value must be greater than LD by 3. And LD you have to check whether this value, that is development length, is less than 1.3 m1 upon B plus L naught. Here again, since we are providing alternate bars or bent up bars, so we can take this m1 value is equal to 50% of the m1 value which we have calculated the mid of the slab. So next step is the reinforcement detailing, where we have to show all the details. What are the maximum possible detail we can show? So this is the design detailing, reinforcement detailing for simply supported two-way RCC slab. And first of all, now you have to refer here more carefully so that we can understand what is the steel reinforcement detailing here. Now you can see this is a slab which is a simply supported type of slab, and this slab is supported on walls basically, and the center to center span length we can take Ly as well as Lx. So Lx is the length of the shorter span and Ly is the length of the longer span. Now we are going to provide here reinforcement. So you can see black color bars which we have provided, and every alternate bar is bent up. Now this bar is straight bar, and here it is bent up bar, another bar. And on the other side, this bar will be taken in straight, and another bar will be taken as bent up bar. So this black color reinforcement is the main reinforcement which we have provided parallel to the shorter span, that is more critical type of span. And similarly, from here you can see the red bars. These bars are provided to take care of bending moment along y direction, that is along longer span. So again, alternative bars you can see they are bent up bars we have provided. Now for more detailing, we can take two sections. One section is section AA, so that we can see in this direction at this level, at this section, and another section we have taken that is parallel to longer span, that is section BB. So first of all, this is section AA. Now you can see here this black color bar is taken at the lower level because it is the main reinforcement along shorter span, which is more critical. So here you have to take into consideration that since you are providing reinforcement in two layers, so main reinforcement along a shorter span will be taken at the lower level, and above that the reinforcement in the longer span will be provided. So this black color bar, you can see this is reinforcement parallel to shorter span, that is we have calculated for bending moment, that is mx. And this red color dotted which you can see, these are the bars which are provided in perpendicular direction to the shorter span, that is parallel to longer span. And these bars are bent up bars which we have provided, that means these bars, alternative bars, we have bent up. And other information we have already discussed. And this is section BV. Here you can see these black dots are showing the reinforcement which is parallel to shorter span. So when you take the section in this direction, you will be able to see only the cross section of the reinforcement which is parallel to the shorter span. And above this reinforcement, another layer of reinforcement that is parallel to longer span. So that's why we have taken red color for more differentiation. And these bars are bent up again. So you can easily understand that how to find out all the details and how you have to present reinforcement detailing in such a way. Thank you.